Okay, so let's continue our discussion of how this locate query works. We've already discussed this relationship between text space and lex space, and we talked about how some of the functions that we like to compute, like LF, represent predictable movements through part of this and unpredictable movements through other parts. So for example, LF is moving to the left by 1 with respect to t, but it's moving around kind of unpredictably with respect to lex space. And we're going to use LF in this lecture. Okay, so like I said in the previous video, this locate query algorithm has two components, and we've already discussed the first one, where the first component is that we want to track our toehold. In other words, as we make our movements, we always want to maintain some correspondence between one of the rows that we're tracking in lex space and its corresponding suffix array value, which is to say what offset it corresponds to in t space. So we'll always have one tether between the two spaces, between lex space and t space. We already saw how to do that. Now, the question is, from that tether, can we get the answer to our larger question? Because the larger question is the answer to a locate query. Perhaps we've done a search, we've found the range of rows that have our query as a prefix. Now we want to report all the offsets, right? The offsets for all those elements in that range, the suffix array entries, in other words, for all the elements in that range. And the way we're going to do this is by starting at our toehold value, which we already know, and moving outward and reporting all the other values. So we know that the BWT of t, so the thing labeled L on this slide, consists of runs when t is repetitive, right? It consists of relatively long equal letter runs. So we can think of dividing L up into its constituent runs as something like a parse of L. It's like we're taking L and dividing it up into phrases where the phrases are the runs. And we saw a picture like the one that's on the screen right now in the previous lecture talking about how we maintain our toehold. Now we want to talk about a way of parsing t. So we're going to parse t this time. But we're still going to use the run heads and tails in order to parse t, right? But t doesn't consist of these same equal letter runs, right? It's not like L in that respect. But still, we will take the run heads and tails from L, and then we'll find the run heads and tails counterparts in t, and we'll use those to divide up t into phrases, right? So we're going to sort of, in some sense, if L is where the permutation is taking the letters of t, we're going to do the reverse permutation to get back the letters of t that corresponded to the run heads and tails in L. So let's do that sort of step by step. Let's start with the very first run's head. So we're going to take that t and we're going to recall, okay, well, what's the offset of the t in the original text that actually got permuted to that position of L? And the answer is it's at offset 62. It's at this t over here. And so we're going to mark that, right? Like this t here corresponds to this t here. And because this t is a run head, we're going to mark it. So we'll mark this R similarly, and we'll mark this W and this O, and we'll just keep marking stuff in red according to whether it's a run head in L. And we're not done because we'll do the same thing for the run tails as well. So let's mark some more according to whether they are run tails. So we just marked well, I guess we'd already marked that first T, but we marked an R and a W, and now boom, we mark every run head or tail. We mark the letter in T that corresponds to that run head or tail, that got permuted to that run head or tail. And so now we have several marked letters in T. We're going to mark one more letter, which is the first one. So just as a matter of policy, you'll see that these are going to turn out to be the phrase beginnings. So we want to make sure there's always a phrase beginning at the beginning. So we also mark that very first letter of T. And we're going to let each of these positions begin a new phrase. Okay, so now let me change the picture a little bit so you can sort of see the phrases. So I've got the beginnings of the phrases marked in one color, so marked in red. And then I've got everything else in the phrase, after the first letter of the phrase, marked in green. So sometimes you'll see a bunch of red consecutively, and that's because those phrases are only one letter long, right? So there's no green because there's nothing that comes after the head in those cases. Okay, and I'm showing these sort of dark black vertical lines separating these phrases, but that's a little bit distracting. So I'm just going to turn it into these sort of white lines, sort of so that the phrases look like they have a little bit of space between them. Okay, so one of these is called a phrase or just a T phrase. And then the first letter is called the phrase head. Our next task is to associate suffix array samples with the phrase heads. And actually, with each phrase head, we're going to associate two different suffix array samples. Okay, so let's go into the specifics. So let's just take one example. So here I've got highlighted in L, I've highlighted this letter T. This T in L corresponds to this T in T. And so if we were to take the suffix array entry for this T, we would find that it points here to the right context of this T, right? And so if we just go over to the left by one, we'll find the T that corresponds to this T. Okay, so you can think of Q here. We'll usually use Q to denote an offset into L, and then we'll use I to denote an offset in T. So Q represents the lex rank of T of I's right context, right? So T of I's right context has rank 38. Or another way to say that is I is just what we would get if we took the suffix array entry at 38, which again points us here, and then went over to the left by 1, right? Minus 1. Okay, so this could be the tether. This could be the toe hold that we have. Like it could be that we're tracking a range that includes offset 38, and therefore our toe hold is linking offset 38 in the BWT to offset 20 in the text T. Okay? All right. So what we want to do is with this phrase head, again, we're talking about T phrases here. So if you remember, so the phrase I'm talking about is, this phrase, right? So with the phrase head, we want to associate two suffix array values. The ones corresponding to the letters of the BWT that are on either side of the one that is our kind of toe hold pivot. Right, so if Q38, offset 38 with respect to the BWT is our kind of pivot, it's our kind of focus, then what we want to store at its corresponding phrase head is the suffix array entries for my neighbors to either side. Right, what's the suffix array entry for the next smallest suffix in lex space, and what's the suffix array entry for the next largest suffix in lex space? Okay, so in this example, what would we store? Okay, well, we have to go look for what's the suffix array entry at Q minus 1, in other words, offset 37 into the suffix array, and what's the suffix array entry at offset 39? Okay, well, it's hard to see that just by looking at this picture, so let's just go take a quick look at the Burrows-Wheeler matrix. Okay, it's still hard to see because the Burrows matrix is pretty big, so let's just zoom in on the relevant rows. And here they are. I've sort of drawn a gray bar for the row corresponding to our anchor, our pivot, our toe hold. Right, so this is our toe hold. And here are the suffix array entries for the suffixes on either side in lex space. 42 and 0. So the suffix array at Q minus 1 is 42. The suffix array at Q plus 1 is 0. So that's what we would store here, associated with the run head. 42, 0, the phrase head, I should have said. 42, 0. Okay, so again, those are just the suffix array entries for the suffixes that are one smaller and one larger in lex space. Let's pick a different toe hold this time. So let's pick the toe hold at offset 15. That also corresponds to a phrase head. So that's this O right here. And so at that O, we want to store the two suffix array values for our neighbors in lex space to the left and right. And in this case, we need to again go look them up. And this would be 40 and 59. 40 and 59. So if we just go ahead and do this for every phrase head, then we end up with a big table that looks like this. Okay? And we call this table N. And so I'm arranging this table sort of horizontally here to correspond to T. But you can see this first entry in the table is the offset of the phrase head. These are all the phrase head offsets here in this row labeled I. And then for each of those, we of course store what's the suffix array entry for the suffixes that are one smaller and one greater. So this is going to be an important table that allows us to answer locate queries that radiate out from our toehold, right? We want to radiate out and answer locate queries for our neighbors to the left and right, and then their neighbors, and then their neighbors, until we've filled out the entire set of locate queries. But how do we do that? So how do we use this N table to answer arbitrary queries of the form, okay, given that I'm at offset Q with respect to the BWT, please tell me the suffix array entries for my neighbors on either side. We want to be able to answer that query for arbitrary values of Q, not just the ones that correspond nicely to these phrase heads, but all the ones in between as well. So that's what we'll see in the next video. And just as a preview, we're going to use LF mapping to sort of move to the left with respect to T until we get to an entry for which we do have the recorded suffix array values. And then we're going to do a little computation to figure out what the answer to our original question was. And we also are going to have to come up with at least one idea for how to do this quickly so that we don't have to iterate LF mappings. So that's coming up in the next video.